Okay, so here let's take a look at this sample problem. So it says a plastic rod having a uniform distributed charge, negative Q. So rather than the whole ring, we only have a part of the ring, which is an arc, and there is a charge negative Q equally distributed on this arc. The rod has been bent in a 120 circular arc of radius r. So this is r, and we place the coordinate axis such that the symmetric, the axis of the symmetric of the rod lies on the x-axis. So totally 120 degree, and then 60 degree for the negative part, and the next 60 degree for the positive part. So yeah, so the origin is at the center of the curvature P of the rod. In terms of Q and R, what is the electric field E to the rod at the point P? Okay, so let's see. So similar to the whole ring, we also separate this ring, this arc into many small segments, just like this one is ds, and of course on it there on this segment we have a small amount of charge dq. Yeah. Okay, so similarly, we also define the density. The density of the charge is lambda. So we will have the relationship as dq equals lambda times ds. So this is the charge amount on this part, and this is the line charge density, and then multiplied by the length. The length multiplied by the length density will be the charge amount. Okay, so in this case, the dE generated by this small segment on point P, which is the center of this arc, will be dE equals K times dq over the radius. Radius is small r, as mentioned here. Radius r. Okay, so r squared, like this. So nothing special. And of course this charge is negative Q, so for this part the dE should pointing towards this ds rather than pointing to the bottom left. Okay, so this is dE, and also we can still find this symmetric part right here, which is called ds prime. So ds prime will have the same amount of charge because the charge is uniformly distributed, and also this is an arc. So point P, the distance from point P to ds and the distance from point P to ds prime will be the same, also r. So dE prime will have the same magnitude, but the direction are different. So dE points to the top right, and dE prime points to bottom right. And simply speaking, you can see that the vertical component dEy prime will cancel each other. So only the horizontal component will be added together. Okay, so actually dEx, so we call this dEx will be K times dq is this one. So we have a lambda ds here over r square, and cosine of theta. Theta is theta is this angle, the angle from x-axis to DE. Yeah. Okay, so this is cosine of theta because yeah, DE, this one divided by this one is cosine theta. Okay. So and the next step is we have ds should be r d theta. I suppose you should have learned this in high school mathematics. So this is just like something like, yeah, like this. So this angle is theta, and this is the radius. So the arc length will be r theta, and of course in this case, we will have something like this is ds. So actually this is d theta. So ds is r times d theta, like this, which is this case. Okay, so we can just plug this one into here. So we have a k r lambda over r square cosine of theta d theta, and we can cancel this r and this r square, so it becomes a k lambda over r cosine of theta d theta. Okay, so this is dex. This is dex, and finally we can find the overall E field generated by the whole arc by integrating dex. So we can just put this part here, and we have k lambda over r cosine of theta d theta. And of course we need to determine the lower bound and the upper bound for this integration. It should be a definite integral. So this is x-axis, and this is theta. So it starts from negative 60 degree to 60 degree, or in radian it should be like pi over 3, negative pi over 3 to pi over 3 in radian. Or you know, in calculus we usually use a radian rather than degree. So we put pi over 3 here and negative pi over 3 for the lower bound. Okay, so actually k is constant, lambda is constant, r is also constant for this arc. So we only have the integration of cosine theta d theta, which is easy, I think. So we have a k lambda over r integration of pi over 3, negative pi over 3, cosine theta d theta. So the antiderivative of the cosine of theta should be sine of theta, which means we have a k lambda over r and then sine of theta. We evaluate it from negative pi over 3 to pi over 3, right? So it is k pi, or maybe we can start to plug in the values. So k is 8.99 times 10 to the 9th power. This is k. And then lambda, we don't have, or maybe we can still keep this one to have a closed form solution. So let us just keep this k prime k lambda over r here, and then sine of we have sine of pi over 3, which is square root of 3 over 2 minus negative square root of 3 over 2. So altogether we have square root of 3 here. Square root of 3 k lambda over r. And yeah, and actually we actually need to remove or eliminate this lambda, because lambda is not given here. It only provides the Q to us. So actually the whole length of this arc is this is 120 degree, which is 2 pi over 3, 2 pi over 3, which is the angle, and then multiplied by the r, by the small r, will be the length, and then it multiplied by, so this is the length, this is the length of the arc, multiplied by the density, will be the charge, amount, like this. Okay, so we can find that lambda should be 3q over 2 pi r, 3q over 2 pi r. So we have a lambda equals 3q over 2 pi r, and then we plug this one here, so we finally get 3 times square root of 3 kq over 2 pi r squared, like this. Is it? Yeah, it's this. Yeah, this is the case. Yeah, like this. Okay, any questions? I just, yeah, actually I can, yeah. Okay, so if there's no question, let's move to this checkpoint. This checkpoint is just let you somehow familiar with how we can use the cancellation technique to simplify the calculation. Yeah, so here it says there are 3 figures, and then we have a negative q, which is indicated by right color, and then positive charge indicated by dark color, and then it asks you what is the direction of the net electric field at point P. We don't really need to do any calculation, but yeah, we just need to determine the direction of the E field at point P. So yeah, so let's go through it quickly. So for the part A, the E field generated by this part, what is the direction? What is the direction? Regarding to negative Q, let me make it large enough. So what is the direction of the E field generated at point P regarding to negative Q? Top right, top left, top left. Okay. Actually, it's 45 degrees with this negative x-axis. Okay. So how about this part? So this is 45 degrees. Okay. So for this one, top right. So the overall direction, pointing upward, like this, pointing upward. Okay. For this one. for the upper part, it should somehow pointing there. I don't actually know the angle, yeah, because it should relate it to this height and the distance, but it should somehow point to the bottom right, because this is a positive charge. It should pointing somewhere there. And then actually this is symmetric. We should suppose this height and this height should be the same. So for this part, it should pointing top right, pointing to the top right, and of course the overall direction should be point to the right side. So this is pointing upward. This is pointing to the right side, IGHT. And then for the last one, for this part, it should be the same as this case. It should point to the bottom right. And for this part, this is negative charge. So it should point to the bottom left. So overall, it should pointing downward. Downward. W-A-R-D. Downward. Okay, any questions? Okay, so let's move on to the next case. So just now we actually the last lecture we introduced how to calculate the E field generated by the ring. So here it also introduced how we can actually find the E field generated by the solid disk, the charge disk on this axis. So the definition of this axis is actually the same as the ring. The only difference is that this is a solid disk. And the charge is also uniformly distributed on this disk. And it actually tells you that so we still need to separate this disk into many small parts. So so when you learn calculus, maybe you should, I'm not sure I'm not sure whether you have learned the integration to maybe find the area of a circle. If you just say if you need to find the area of a circle, so this is x squared plus y squared equals r squared, something like this. And for this part it should be y equals square root of r squared minus x squared. So it is like you try to separate this circle using the Cartesian coordinate. And for this case, we still need to separate it into something like that. And if you have ever learned this integration, the integration of r square root of r squared minus x squared dx from negative r to 2r will be the area of the half circle, and then multiplied by 2 will be the whole area of the circle, right? And so you feel that this integration is not so easy. You need to substitute x into r times sine of x, and then do many calculations, which is not so trivial. So here we will use something called the polar coordinate. Okay, polar coordinate is like the 极坐标嘛. In Chinese it's called 极坐标. Okay, so we will try to separate this circle. Actually, this is actually a circle. So we try to separate the disk like this. this. So this is separate into many rings, many rings. Each one is a ring, and then with different radius, and then this ring construct to a whole disk, something like that. Okay, and as much as we have already know how to find the E field generated by a ring, we don't really need to further cut this one. Ouch. No, we don't really need to further. Maybe I use another color. I don't know. Yeah, we don't really need to cut it in the angle, because for polar coordinate, actually for Cartesian coordinate, we have x, y for two dimension, or x, y, z in 3 dimension. For polar coordinate, we have r and theta, something like this point is, this is r, this is theta, so this point is r theta, something like this. So if we further need to suppose we don't know how to we don't know the result for the E field generated by the whole ring, we actually need to further cut it into many different angle, something like this, so that each one is a small packet of a charge, and then we can apply dE equals k times dq over r squared, something like that. Okay, so this is the case. We use the rings with different radius to construct the whole disk, and then we try to integrate the radius from 0 to capital R, which is the radius of the disk, to find the whole E field generated by the whole disk. Okay, so just now we already know that E is k times qz over this term to the 3/2 power, and now we still regarding this part is dq, so we replace this q to be dq, and then this e to be de. And the other thing, yeah, we also make r to be small r, because we need to integrate this small r from 0 to capital R. Capital R is for the radius of the disk. Okay. So we make these 3 tiny change, so nothing special here. And so the next step is do the integration. But before doing the integration, we need to do some variable substitution, because now dq, we cannot directly integrate over dq, because we can imagine that we should integrate dr from 0 to capital R. So we need to do some change of variables. Okay, so here dq is the total charge, and actually this is a ring, so it should has an area rather than a length. So sigma here is the surface charge density rather than length charge density. So it should has a SI unit of C over M squared. So this is the surface charge density multiplied by the small area of this ring, and the area of this ring is this one, 2 pi r dr. How it will be like that? The reason is you can try to cut this ring. You can try to cut this ring here, and then you try to expand it into a rectangle. It is not so trivial, but yeah, suppose this ring is very thin, so you can try to imagine the length of the inner border and the outer border have a similar length. So when you try to cut it out and try to expand it, so it will be a rectangle. It will be a rectangle. So the length, so the width of the rectangle will be the circumference of this circle, which is 2 pi r. And then the thickness of the ring will be the height of this rectangle. So this height will be dr. So this is dA. This is dA will be 2 pi r dr. Like this, like this. Like this. Okay, so we can just replace dq by this whole term. So it looks like this. So sigma 2 pi r dr, sigma 2 pi r dr here. And then we still have z here, and then also have this term. Okay, so we try to slightly rearrange the terms so that, and actually we can do some cancellation. We have 2 pi here, partly cancel with 4 pi, so we have 2 here, and or maybe I actually still keep this 2, still keep this 1. I only cancel pi here. And then we move z to the front because z is not related to r. So z is just a constant. So I just put z and sigma to the front. Sigma z to here. And then we have 4 epsilon naught here. Okay, to the front. And then we have 2r dr. 2r dr, and then we have this big term there. So like this. Okay, so next we can do the integration, which is actually the total E field, which is integration of dE, which is actually this one, and this is constant. This whole term related to r, so we need to do the integration of this one, but it is not so difficult. So yeah, actually E is this one, and then this is a constant, so we just move it out from the integration. And actually doing the integration of this one is not so difficult because we can use the chain rule. Or you can regard it as a change of variable. So 2r dr is nothing but dr square. Or if you are only familiar with the derivative, it is like dr square. Dr equals 2r. Yeah, I suppose you should get to know this one very easily. So if you move this one to the right side, it will be 2r dr equals dr square. So z square is nothing but a constant. So we can just put the z square here, because z square is just a constant. If we just take the derivative of a constant, then it will be 0. So we just put it there. So this 2r dr becomes this one, dr square plus z square. Then we can use we can just regard it as a variable, as a new variable, and do the integration, which is just the polynomial function. So we add the power, add 1 to the power, so -3/2 becomes -1/2, and then divide this number, -1/2 here. And then we evaluate this one from 0 to capital R, like this. Okay, so we can, yeah, so this 2 and this 4 can be cancelled, can be partly cancelled. So we have a 2 here, 2 epsilon naught sigma z squared. And then we try to plug in the things. Because we have a negative sign, so we just put in 0 in this expression. Actually, here we should have R to be 0, R to be capital R. So let's just put R to be 0. So we have 0 square plus R square, and then take the negative 1 over 2 power, which becomes this term, and then minus, because we have a minus sign, so we just swap the lower and upper bound. So and then we plug in R to be R, capital R square. So we have a C square plus capital R square, and then take the square root in the denominator, like this. Okay. So finally, we can just distribute this z into here and into here. So this z and this square root of z square will cancel each other, and then this one we have a z over square root of a z square plus R square, like this. So this is the closed form solution. Closed form solution. When we consider a disk, the E field generated on this axis will be like this. Okay, so we get this expression, and then also we have an assumption. This is an assumption. If capital R is infinitely large, if capital R is infinitely large, which means that this disk is very, very large, infinite disk. In this case, if z tends to capital R tends to infinity. This case is capital R tends to infinity of this one. So this one, the first term is constant, so nothing special. For this one, which is like negative 1 over square root of 1 plus R over Z square, like this. Should be like this. So R is infinity. So the denominator is infinity. So the whole term is 0, right? So this whole term turns to 0. So if we have this assumption, E is only the first term, sigma over 2 epsilon naught. Sigma over 2 epsilon naught. So which is a very elegant solution, because this is a constant, which means that if this disk is infinitely large, it will generate the E field uniformly. It does not depend on the distance between the point we concern with the plate. So this is a uniform E field generated by the infinitely large plate. And actually, this is related to the capacitor. Related to the capacitor. If we have two parallel plates, then it will be capacitor. And yeah, and some characteristic will depend on this one. So we will actually see it again in the chapter 23. Actually, the next chapter, and also in chapter 25 when we talk about the capacitor. Okay, so far any questions? Okay, so here is an application of the parallel plate. So it's called a point charge in the electric field. So actually this is a diagram, a simplified diagram for the inkjet printer. So it says there is a parallel plate here, and then we can just put some charge. Suppose it's uniformly distributed on these two plates. One is positive charge, one is negative charge. So it will generate the E field pointing perpendicular to the plate. And of course, this is not infinitely large, but if you just consider the space between these two plates, it will be approximately uniform inside this region. So the idea for the inkjet printer is like this is supposed to be the green color. The green color, it try to inject an ink to the right side, and here is the input signal to control how many charge we put on the ink. So suppose it has a charge negative Q, and then suppose this is parallel plate and this is a plus, this is plus 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 plus, this is minus minus minus, positive charge and negative charge. So there will be E field pointing downward in this region, E field pointing downward. Okay, so suppose the ink goes to here. It has a charge of it has a negative charge, negative Q. So due to the Coulomb's force, which is F equals negative QE, negative QE. Q is a positive value, so this is negative. So negative QE will be pointing upward. So it's just like what you have learned in high school physics. You learn the suppose you throw a thing to the right side, and then with initial velocity, and suppose the velocity doesn't change, and then this object will be accelerated by the gravitational force. So we have a mg, by the gravitational force. So you need to find the locus, or something like that. So it is actually like the case, but here we just ignore the gravitational force. The main force is the electrostatic force or electromagnetic force, something like that. So there will be a locus going to the right side and slightly upper. So, and then suppose we try to control the charge put on the ink, it will affect the position, the angle to the paper, like that. So this is a simplified model for the inkjet printer, like that. Okay, so here is a sample problem. So it says the deflecting plate on an inkjet printer with a superimposed coordinate axis and in an ink drop with a mass blah 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 and a negative charge of Q, capital Q, enters the region between the plate, initially moving along the x-axis with speed Vx. The length L of each plate is 1.6 centimeter from here to here. This is the length. The plates are charged and thus produce an E field at all points between them. Assume the field is downward directed, uniform, and has a magnitude of blah blah blah. What is the vertical direction of the drop at the far edge of the plate? So ask you this height. Okay, so the gravitational force on the drop can be neglected. Okay, so it's just like some high school physics problem. So here we try to consider the time it takes the drop go from here to here. It takes some time, so this time is like the length over the speed Vx, because the Vx doesn't change. So yeah, so L is 1.6 centimeter. L is 1.6 centimeter. And yeah, and of course you should be careful about the unit. The SI unit should be meter rather than centimeter. So we should convert it back to meter. Okay, 0.016 over 18 meter per second. 18 meter per second. So this number is, oh, it's a good number, which is 8.89 times 10 to negative 4 second. So this number is, yeah, the same as the number of K. And now we need to calculate the force acting on this charge or the ink. So F equals QE will be Q. Maybe I can use capital Q here because we have capital Q here. And yeah, and also the E field is this one. The E field is this one. So we have 1.5 times 10 to negative 13 times 1.4 times 10 to the 6th power, which is 2.1 times 10 to negative 7 Newton. Okay. And next, y should be half of at squared. Half of at squared. It is some sort of high school physics. So and using the Newton's law of motion, we know F equals ma. So we have F over 2 m t squared, like this. So F is actually this one, 2.1 times 10 to negative 7 over 2 times m. M is here. 1.3 times 10 to negative 10 times T. T is this one. 8.89 times 10 to negative 4 quantity square. So the answer will be 6.4 times 10 to negative 4 meter. So usually for the scientific notation, this number should be between 1 and 10. Can be larger or equal to 1 and smaller than 10. So yeah. And yeah. And if we would like to write it in using the scientific prefix, you can write it as 0.64 millimeter, or maybe you can write it as 640 micrometer. Micrometer, like this. Usually 0 point something is still okay, but we will not write it as 0.06 millimeter. So okay, so here we talk about the dipole in an electric field. So in the beginning of this chapter, we already introduced what is a dipole. So now we talk about when we put a dipole in the electric field, what will happen. So let's take a look at this figure. So this is a dipole. We have a positive charge and a negative charge with the same amount in a small distance, d. So this P is the dipole moment. This P is the dipole moment. Okay, so this is the dipole. P is the dipole moment from the negative charge to the positive charge. Okay, and the magnitude is QD. QD, if you still remember, P equals QD. Okay, so now suppose the angle the angle between the dipole and the E field. Suppose the E field is uniform and pointing to the right side, and the angle between the E field and the dipole is theta. So we can see this is a positive charge, and then the E field point to the right side. So the electrostatic force acting on this positive charge will also point to the right side. Okay. Okay, just look at the right side. I don't know how to fix this one, but at least we have the wide screen. Okay. Okay. So for the negative charge, as it is negative charge, the electrostatic force is opposite to the direction of the E field. So the force acting on the positive charge point to the right side, the force acting on this negative charge point to the left side. So it is like this. So it will start to rotate like this, because you try to drag this one to the right side, drag this one to the left side. So you just start to rotate, and actually if there is no loss, it will be like the pendulum, the pendulum, which is like from start initially, if there is no velocity, and then it will be like this, swinging with to the angle negative theta, and then swinging back and forth, something like this, like a pendulum. Okay, so actually in the mechanics, you know, suppose we have the force, we have a force acting on an object with length. So we have a variable called the torque, The torque on the electric dipole of electric dipole moment P will be defined as this. The torque is P cross E. So the P point to the top right direction, and then the E points to the right side. So in high school physics, you should already know the right hand rule, but yeah, actually it's like you use your forefinger pointing to the P, and then you try to rotate it to E, and then your direction of your thumb is actually the cross product, the torque. So actually the torque like this, the torque here. So this cross means this vector is pointing into the page. So into the page. If it is like this, it is out of the page. So suppose the direction of the torque is into the page, which means that there's something rotating like this, which is clockwise. If it is pointing out of the page, then there must be something rotating like this, which is counterclockwise. Okay, so this is the torque, and actually we will talk about the cross product later when we talk about the magnetism. Yeah, so the next part is the potential energy. Related to the torque, we have the potential energy U to be negative P dot E. So this is the inner product, which is like P times E cosine of theta. Yeah, theta is the angle between the two vectors, and we have a negative sign. We have a negative sign, so it will be like if theta is 0 degree, which means that the dipole has the same direction as the E field, So cosine of 0 degree is 1, and then it takes the minimum value because we have a negative sign here. So it will be negative PE, which is the minimum potential energy. Potential energy. If it is if theta, so it is a minimum potential energy to be negative PE. If theta is 180 degree, then it will be the maximum potential energy will be positive PE, because these are constant and cosine of theta should be between -1 and +1. So yeah, so it will be like that. And the point is like if the dipole is initially with the same direction of the E field, then it will not move, it just hold there. And if it is the other way around, the dipole points to the left side. So suppose it is not if it's disturbed by something, then it will start to swinging back and forth like that. Swinging like hard to demonstrate it for 180 degree. But if it is like 90 degree, it will be like swinging to the bottom and then going back and forth like this. So you can imagine that if it is 180 degree, it will swing in the most large scale. So which means that it has a largest potential energy, which is like if you have a curvature and then you have a ball, you just put it there, then the ball don't move at all. But if you have a curvature, if you put a ball here, then suppose there is no loss, then it will going to the bottom and then going to the left side and then going back and forth like this. Okay, so here we have two additional example. So as mentioned, I will just finish this part before we have a break. So this one says a clock face has negative point charge, negative Q, negative 2Q up to negative 12Q, fixed at the position and the corresponding numerals, like the clock. No clock. Okay. So the clock hands do not disturb the net field due to the point charge. At what time does the hour hand point in the same direction as the electric field vectors at the center of the dial? Hinge symmetric. Okay, so this one will be easy. Okay, so suppose we have a clock face like this, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So suppose it says for 1 we have negative Q, for 2 we have negative 2Q, so on and so forth. Let me write some of that. I don't try to write or. So up to here is negative 12Q, and then so on and so forth. So it asks you what is the overall E field generate at the center point. So the point here is that we can use the cancellation. Okay, so let us try how to use the cancellation. So for 1, we have a negative q, and for 7, we have a negative 7q. So you can imagine part of them will cancel each other, because for negative q, the E field generated by it will point to the upper right, top right, and the E field generated by negative 7q will point to the bottom left. So part of it will cancel, so it will become like something like, it should be equivalent, something like we only have negative 6q here. We only have negative 6q here. So after the cancellation, this one and this one will generate the same E field at this point only. For other points, it is not the same case. But at least for these points, it is cancelled like that. And so on and so forth, we can also cancel these 2 and 8, 3 and 9, 4 and 10. Like we have negative 6q there, negative 6q there, negative 6q, negative 6q. Whoa. 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 Oh, negative 6q, negative 6q. So from 7 to 12, we have negative 6q all the way. So finally, the overall E field should point to here. Actually, between 9 and 10. So it asks you at what time it should be. It should be 9:30. It should be 9:30. Because we should have something point to here, to here, to here, to here, to here, to here. So the overall E field should somehow point to this direction. Okay, so we okay, so we have another additional example, and I suppose we can finish it quickly. So suppose you design an apparatus in which a uniform charge disk of radius r to produce the electric field like this one. The field magnitude is most important along the central perpendicular axis of the disk at a point P at distance 2r from the disk. So this is 2r. Cost analysis suggests that you switch to a ring of the same outer radius r, but with inner radius r over 2. Not that r. I think this one is 2r. This one is 2r. And then here, this one is r. This one is still 2r. Yeah. So 2r for the whole disk, and then now try to remove the inner circle with radius r, and actually the whole circle is still 2r. So assume that the ring will have the same surface charge density as the original disk. If you switch to the ring by the percentage, will you decrease by what percentage will you decrease the electric field magnitude at P? Okay, so if you still remember, for the E field generated by charge disk, it should be something like E equals sigma over 2 epsilon naught 1 minus Z over C squared plus capital R squared. If you still remember, actually you don't really need to remember, because it will be provided by you during the quiz or exam. Okay, so maybe we call this one A. So EA will be sigma over 2 epsilon naught times 1 minus this z, this is still 2r, this is still 2r. Okay, so this z should be 2r, and then over square root of z is 2r also, so 2r quantity square plus r squared, like this. So r and r square, r and r can be cancelled, so it turns out to be sigma over 2 epsilon naught 1 minus 2 over square root of 5, because we have a 2 square, which is 4 plus 1, so square root of 5 and then 2 here. Okay, so next we consider the E field generated by the hollow part, which is actually sigma over 2 epsilon naught 1 minus here oh, sorry, this radius should be r, this is 2r, and actually this radius is r, and the small one is r over 2. It's r over 2. Okay, so here for the hollow part, z is still 2r, this is 2r, this is 2r quantity square, and this r now is the smallest one, which has a radius of capital R over 2. So here we have capital R over 2 quantity square, like this. So this value will be sigma over 2 epsilon naught 1 minus 4 over square root of 7. So it asks what percentage you decrease the E field, so it will be E hollow over EA, which is sigma over 2 epsilon naught 1 minus 4 over square root of 7, all over sigma over 2 epsilon naught 1 minus 2 over square root of 5, and then multiply by 100%, so it will be 28.3%. Yeah, because the area here is smaller than the outer part. For the inner circle, it only occupies 1/4 of the area. But distance from this part is slightly closer to there, so it is slightly larger than 1/4. Okay, so any questions? If no question, let's have a 10 minutes break.